Hi everyone, I'm Dr. Bonnie Light and I'm a research scientist here at the Polar Science Center at the Applied Physics Laboratory at the University of Washington in Seattle, Washington. I study the physics of sea ice, specifically how the sea ice cover melts during summer. I'm keenly interested in how sunlight is partitioned by sea ice, that is to say, how the sea ice reflects, absorbs, and transmits sunlight. This partitioning is key to understanding how the ice cover melts every summer. It's also central to Earth's heat budget, and it plays a really important role in Earth's climate. I'm a member of the MOSAiC Sea Ice team, and we'll be making measurements at the MOSAiC Ice Station during the summer melt season. And unfortunately, we can't get our hands wet or cold together in this video lecture. But I invite you to join me in thinking about the role of sunlight in the Arctic system. So, if you were hanging out at the North Pole, once a year you'd witness a long, slow sunrise. It would happen on the vernal equinox, which is late March in the Northern Hemisphere. All summer long, the sun would be above the horizon for 24 hours a day, 7 days a week. Now that is one long day, and that's a lot of sunlight. You'd have to wait 6 months until the autumnal equinox to watch the sunset. And if you were hanging out at the North Pole, what do you think you'd be standing on? Sea ice. Now, the physics of sea ice growth and formation are pretty well understood. Every autumn, sunlight wanes, the Arctic atmosphere cools down quickly, the uppermost part of the ocean begins to cool to its freezing temperature, and then sea ice begins to grow. But the physics of sea ice melt and retreat are a bit more complicated. And that's where sunlight and the long days of summer get really interesting. If you went outside on a sunny winter day, if there was little or no wind, the sunlight might start to feel really warm on your face, even if the air is cold. Now that tells us that there's energy in sunlight. And where that energy is absorbed, it can become heat. Sunlight that falls on the Arctic contains enough energy to fuel photosynthesis to support an entire ecosystem, to melt significant amounts of sea ice, and to measurably warm the upper ocean. In recent years, the amount of ice that melts each summer has been increasing, and it's understood that this trend depends on many factors. One factor is what the sea ice cover does with all this sunlight. In part, we quantify the partitioning of sunlight by a surface by measuring something called the albedo. The albedo is a fraction between 0 and 1, and it's defined as the ratio of reflected light relative to incident light. If a surface has albedo equal to 1, then it's perfectly reflecting. An albedo of 0 would describe a completely absorbing surface. Each winter, snow accumulates on top of Arctic sea ice. Cold, dry snow is very effective at reflecting sunlight. It has an albedo typically greater than 0.8. When the sun rises each spring, the surface albedo is high. Most of the sun's energy is reflected and very little is absorbed. But as spring progresses, things start to change. Increasing air temperature and increasing sunlight begin to melt the snow. As warming occurs, individual snow grains enlarge and become more rounded. Eventually, the snowpack starts to melt and liquid water forms. These changes reduce the albedo of the snow cover, which increases the absorption of heat. And as melting increases, liquid water is produced. Some of the meltwater runs off the ice cover, drains into cracks or over the edges of the ice floes. But some accumulates in puddles on the ice surface. We call these puddles melt ponds. And they typically start out as gray areas on the ice surface. But as they deepen, they turn many different shades of blue. Over the course of the summer, 3 distinct surface types develop on a melting ice cover: bare ice, ponded ice, and open water. Bare melting ice appears white. Its albedo remains about 0.6 to 0.7 through the entire summer. The reason it appears white is, just like snow, it also reflects light very effectively. This high reflection is due to tiny pockets of liquid water and air bubbles within the ice. And these inclusions are tiny. More than 20 of them can fit in a cubic millimeter, which is smaller than the tip of your pinky finger. Sea ice reflects light because the brine and air inclusions have different material properties than the surrounding pure ice. And these discontinuities cause light rays to bend or scatter. If rays are scattered enough times, they can eventually be redirected right back up to the atmosphere. The more rays that are scattered upwards from a surface, the higher the albedo of that surface. And it's worth pointing out that each of us is equipped with a set of really good optical detectors. These are our own eyes. If something looks bright to us, then it probably has a high albedo. The only problem with these natural detectors is that they're very difficult, if not impossible, to calibrate. So that's why we use electronic light detection equipment to measure the albedo of various surfaces in the field. So we now know that snow-covered and bare melting sea ice have relatively high albedo. They don't absorb much of the sun's energy. But what about ponded ice? The visual appearance of ponded ice depends partly on the depth of the pond, but mostly on the properties of the ice beneath the pond. If the ice is thick and still contains a lot of brine inclusions and air bubbles, the pond will likely appear medium blue. Ponds on ice with a lot of bubbles will appear lighter blue. If there's some old snow left hanging around on the ice beneath a melt pond, that pond can appear very bright blue. If the ice under the pond is thin, the pond might appear very dark blue, almost black. The appearance of a single melt pond can evolve considerably over the course of a summer and can have albedo anywhere between 0.1 and about 0.5. And then there's the open water between ice floes. It doesn't scatter much light at all. It has the lowest albedo of all, less than 0.1. So here's a question for you. It's going to be a warm, sunny summer day, and you plan to be outside, and you'd really like to stay cool. Are you going to choose the light t-shirt in your closet or the dark t-shirt? I'm going to choose the light one because I know it's going to do a better job of reflecting sunlight, as opposed to the dark one, which could absorb a lot more of the sun's energy. This t-shirt problem is a really good analogy for the Arctic sea ice cover in summer. When two surfaces are made of the same material, in this case water, liquid or frozen, the lighter colored, higher albedo surface absorbs less energy, and less energy means less heat. Snow-covered ice and bare melting ice are like the light t-shirt. They reflect a large portion of the sunlight that falls on them back to the atmosphere. Open water is like the dark t-shirt. It absorbs the most heat. Ponded ice, somewhere in between. So what happens if the snow and ice stick around in the summer? Some of the ice will still melt, but the ocean will stay relatively cool, and sea ice will likely grow rapidly in autumn. In this case, having more ice promotes further ice growth. What happens if the ice melts and exposes more open water? More melt occurs. The ocean warms. Autumn ice could be delayed. In this case, losing ice likely promotes even more ice loss. What I've just described is known as the ice albedo feedback mechanism. It's a positive feedback. Small changes in one direction promote further change in the same direction. And it's a process that's central to our understanding of how the Arctic ice cover melts and retreats. It's difficult to directly measure the ice albedo feedback. There's many variables. There's the sunlight, there's the surface albedo, there's the rate of ice melt, there's lots of different things in a regional area, bright ice, dark ocean. And there's a range of time scales. There's the ice that melts in a day, and there are also seasonal changes involved in the timing of melt onset and fall freeze up. It can be difficult to tease out what's cause and what's effect. But we can measure the pieces, and that's exactly what we intend to do at MOSAiC. We'll be measuring the amount of sunlight incident at the surface, and the amount of sunlight reflected by the surface, and the changes in surface properties of the ice cover through the summer melt season. But the albedo only accounts for the sunlight that's reflected back to the atmosphere. What about the portion that's used to fuel photosynthesis in and beneath the ice? And what about the portion that heats the ocean, If the average albedo of a melting ponded ice cover at the end of summer is 0.4, then that means that the remaining 60% of the sunlight is either absorbed in the ice, used for photosynthesis, or propagated to the ocean. Let's talk about that light. Some of it's taken up by photosynthesis. Sea ice algae and water column phytoplankton experience blooms in the spring and summer. They leave unmistakable footprints in the ice and water with their brown and green appearance. But how does light get through the ice cover into the ocean? And what happens to that light? From above, melt ponds appear darker than the ice surface. But from beneath, melt ponds look like beautiful skylights. They transmit significant amounts of light to the ocean. But where that light is absorbed and how the heat is stored depends on a number of things: the thickness and condition of the ice cover, the extent of melt ponds, and the clarity of the water in the ocean. And there's a lot of really interesting questions we're asking about this topic. We'll be making measurements at MOSAiC to help us get a better handle on some of these questions. Besides measuring surface albedo, we will put light detection instruments beneath the ice to measure the amount of light that propagates through the ice. We call this the transmittance of the ice cover. And just like the positive ice albedo feedback, there's also a positive ice transmittance feedback mechanism. The thinner and younger the ice, the more sunlight that's propagated into the ocean beneath the ice. And the more sunlight in the ocean, the more heat can be absorbed. The more heat absorbed, the faster the ice can melt, and the longer the ice can take to start freezing in the autumn. Just like the ice albedo feedback, it's difficult to measure the whole mechanism at once. But we know how to measure the pieces, and that's exactly what we'll be doing at MOSAiC.